Hello everyone and welcome to section 5.4. So in this section we're going to do more graphing of rational functions. So kind of picking up from the last section. So we're going to put everything together. So there's several steps that you want to go through to get started on the graphing, kind of collect different pieces of information. So basically we want to start by factoring the numerator and denominator as much as we can if it's not factored already. And you want to find the domain of the rational function. Then you're going to reduce the fraction and find the vertical asymptotes. And also if there's any holes. I don't think we're going to do any examples where there are holes in the graph. Then find intercepts. That will give us some points of reference. You want to find any horizontal or oblique asymptotes. So kind of basically building the structure, like the scaffold with the asymptotes. And then the zeros will help. That will find, well, the x and y intercepts are going to come from the zeros, but then you basically use your zeros and asymptotes, vertical asymptotes, to divide up your x-axis into intervals. And then you can pick test points to see where the parts of the graph are. Right? So the function should have a graph everywhere except for where the vertical asymptotes are. So the function is not defined there, so they will not cross this. But it should have a graph for all the other points, because all the other points are in the domain. So you can't leave any of the sections empty. All of them have to have some sort of curve in it. So picking test points will determine kind of how the curve looks like. Is it like above the horizontal asymptote? Is it below? Is it crossing through? So it's several behaviors can happen, and we can verify. We're going to verify with looking at Desmos and seeing if our graph looks like the Desmos graph. Basically, it's a lot of kind of practicing and getting used to the look of them. All right. So let's look at this one. So we have the function r equals x divided by x minus 1, x plus 2, product of those two quotients. So this is already factored, so a is done for us. Alright, let's look at the domain. So the domain here is all the real numbers except for x equals 1 and x equals negative 2. Alright, so part B, reduce the fraction, so nothing reduces. This means that these numbers that are excluded from the domain are our vertical asymptotes. So we have a vertical asymptote at 1 and a vertical asymptote at negative 2. Okay? Now we can start putting these on the graph. Right? So as you kind of work through them, it's good to start building your graph. So let's make our asymptotes in green. So we have a vertical asymptote at x equals 1. Right, so let's put that there. And 1 at negative 2. Let's put that there. So here's 1 and here's negative 2. Alright. Let's find ourselves some intercepts. Okay, so the y-intercept comes from plugging in 0 into the function. Let's see. Let's get this centered. Alright, so r at 0 is going to be 0 divided by negative 1 times 2, which is 0. So our y-intercept is at 0, 0. X-intercept you find by setting this entire thing equal to 0. So x over x minus 1, x plus 2 equal to 0. Right. Now the denominator is going to disappear because if you cross multiply both sides by the denominator, you're multiplying by 0. So you just get x equals 0. So this is our x-intercept at 0, 0. you can see there is only one intercept. Both X and Y intercepts are at 0, 0, that point there. Okay, now let's find the horizontal or oblique asymptotes. So this finds the end behavior. Just so we get polynomials, we looked at the end behavior. Here we look at end behavior by finding horizontal or oblique asymptotes. All right. So let's look at our function, x over x minus 1, x plus 2. Now for horizontal oblique asymptotes, we need to compare the degrees of the top and the bottom. So let's expand the bottom out. So we have x, and in the denominator x squared negative plus 2 plus x minus 2. So we compare the degrees of the leading terms. So the degree of the leading term on the top is 1. The degree of the leading term on the bottom is 2. So because this is less than that, we're going to have a horizontal asymptote at y equals 0. All right, so kind of follow the rules for horizontal and oblique asymptotes that we saw in the last section. All right, so we're going to draw a horizontal asymptote at y 0, which is basically the x-axis. Put the intercept back here. All right, good. So this gives us a structure. All right, so it gives us a structure with the asymptotes, vertical and horizontal asymptotes drawn, and also the intercept. Now, this divides up, so we're going to do this, divide up the x-axis into intervals, and then you pick test points to figure out where the function is. Right? So, you know that for large values of x, positive and negative, the horizontal asymptote says that the function is going to kind of curve and flatten out next to it. But we're not sure whether it's on this side or on this side. So that's why test points are important. So it's like, which one is it? Is it going to be above the horizontal asymptote or below? Right? So, and at this end too. Is it this way or this way? Right? So you can see that this is an important interval that we need to look at. And we go, what's happening at this end? And what's happening next to the vertical asymptote? Okay, next to the vertical asymptote, it doesn't cross it, so the only thing the function can do is shoot up or shoot down. Okay, so you're trying to decide, is it going to be like something like this? Or it shoots up next to the vertical asymptote and then flattens next to the horizontal asymptote, or is it down here? All right, so it can't really do anything else. It's either going to be this or it's going to be that. Okay. Sometimes, occasionally, you'll get a function that sort of will do more things, like it will cross and then it will shoot up. There's more detail to it, but that we're not looking for that level of detail yet. Again, once you sort of start getting to know calculus, you'll get there and you can figure out those turning points. For now, we're more general. Okay. And you can do that without calculus if you pick lots and lots and lots of points. Okay. For simple functions, with the degrees of the numerator and denominator being not very high, it's usually pretty simple. Once they get higher degree, like x cubed, x to the 4th, then you get like more turning points, more wiggles, and you have to be more detailed, more careful. Alright. So let's look at this first interval there. Okay, so we're gonna, as I say, pick some test points. So this is where we are at E. Alright, so I'm going to look at some x values in here. Okay, so let's see what happens for like a large value of x, large negative, and one that's next to the asymptote. Alright, so I'm going to pick r at negative 10. So we have negative 10 over, we're plugging into the function here, negative 11, negative 10 plus 2 is negative 8. So we have negative 10 over 88. Right? And you can evaluate that, but the important thing is that it's negative. Right? So we have negative 10 over 88. It's negative 0.11. Alright, so it's negative and it's pretty small, so we have a point right here. Alright, now let's see what happens close to the vertical asymptote. So pick something like negative 3. So we have negative 3 over negative 4 times negative 1. This is negative 3 over 4, which is negative 0.75. Right, so this one at negative 3, it's about here. Right. Okay, so we can draw that. You can see the horizontal asymptote means this sort of it flattens and kind of gets close to the horizontal asymptote. And I can see I'm going through this point. It's sort of bending down. Right. Well, the only thing that this function can do next to the vertical asymptote, it can't cross it. So you have to basically shoot down next to it like that. And it keeps going down. It sort of hugs that vertical asymptote. Alright, now let's see what happens in the next interval. Let's see what happens here. So again, each part, you're kind of dividing up your coordinate plane by these vertical asymptotes. Each part needs to have a graph in it. There can't be any parts that are blank, alright? So we're going to pick some points. So let's pick a point on either side of the X-intercept, right? So let's plug in x equals negative 1. And we get negative 1 over negative 2 times 1. This is positive 1/2, right? So we get a point here. Right? And let's pick 0.5. So 0.5, negative 0.5 times 2.5. This gives me a negative number, negative 0.4. Right, so we are here. Okay, so you can see that on this side of on the negative side of the X-intercept, it's in the positive region, and on the kind of positive on the other side of the X-intercept is in the negative region. So it's going to look like this. The only thing that the function can be doing close to the vertical asymptotes is either go straight up or straight down. So this is going to continue straight up, and this is going to continue straight down. Right? It's not supposed to cross the vertical asymptote. It's just hard for me to draw them. There we go. Alright, so now let's look in this last region. So we're going to look in this last section of our coordinate plane. We're going to pick some more values in there. So again, pick something close to the vertical asymptote and something relatively large. Right, so I'm going to pick x equals 10 to see what happens for large values. So we have 10, and then 10 minus 1 is 9 times 12. 10 divided by 108 is positive, and it's small, right? It's about positive 0.1. It's like 0.09. So we're here. Okay, so we're already suspecting that the other branch is here. Okay, let's pick something close to the asymptote, like 2. 2 over 1 times 2 plus 2 is 4, so this is 1/2. So positive 1/2, like this. Okay, so our function sort of is flat, right? But once you get close to the vertical asymptote, because it can't cross it, it basically has to continue this increasing upward trend and go next to the vertical asymptote like that. Alright, so this is our graph. Alright, so most kind of rational functions that have vertical asymptotes will have these different sections of these kind of characteristic curves that are caught between the vertical and the horizontal asymptotes. They need to either flatten when you go for large values of x, or they shoot up to positive infinity or shoot down to negative infinity next to the vertical asymptotes. Let's look at the next problem. So same idea here. We're going to start with this and find details and then start graphing it. So part A says factor, right? So this one we can factor r of x equals, actually I'm going to factor it here, 6 over x minus 3 and x plus 2. I'll copy down here too so we can refer to it. Right, so we can find the domain. So the domain is all the real numbers except for x equals 3 and x equals negative 2. Alright, part B says reduce the fractions and find the vertical asymptote. It doesn't reduce. That means both of these excluded values are vertical asymptotes. So x equals 3 and x equals negative 2. Now let's find x and y-intercepts. So we set x equal to 0. And we get 6 over negative 3 times 2. This is 6 over negative 6, which is negative 1. So that's the y-intercept. And the x-intercepts, we need to take 6 over x minus 3 and x plus 2 and set it equal to 0. Right. If you multiply both sides by the denominator, this gives you 6 equals 0, which is not true. So there are no x-intercepts. Right, let's look at D. Find horizontal or oblique asymptotes. So let's go back to the beginning. We're comparing the numerator and denominator. Right, so exponent degree on the top is lower than on the bottom. That means there is a horizontal asymptote at y equals 0. Alright, let's now put all that together and make the scaffold or the structure of our graph. So we're going to put our vertical asymptotes down. So they're at 3 and at negative 2. So 3 and negative 2. Our y-intercept is at 0, negative 1. There are no x-intercepts. And there's a horizontal asymptote at y equals 0. Alright. Now we can see we have these 3 sections that we need to test to see how our function turns. Alright. So in this first section here, our function is either going to fit up top here, right, with that characteristic curve flattening at the horizontal asymptote and shooting up, or it's going to fit down here. Okay, so we don't know which. So we're going to pick, mostly it's enough to pick one test point, but I'm going to go with 2 just to kind of fill in details. Okay, so let's pick negative 10. So we have 6 over negative 13 over negative 8. And that gives me positive 0.06. So it looks like we're up in this region. Alright, and if I pick something next to the vertical asymptote, like negative 3, we get 6 over negative 6 over negative 1, and this gives me positive 1. Alright, so it looks like this. The function here looks like it's in the positive part. Flat here and shooting up to infinity there. Alright, now let's look in the second region, sort of the one between the vertical asymptotes. So I'm going to pick something on the negative side, something on the positive side. Right, so let's have negative 1. we have 6 over negative 4 times 1. This is negative 3 over 2, which is negative 1.5. And something here, let's pick maybe 2. So I have 6 over negative 1 times 4, negative 1.5 again. Alright, so on this side, it looks like it's going down at both ends. Okay, now let's look in this final region for x values bigger than 3. So let me pick x is 10 to go far away from our vertical asymptotes. 6 over 7 over 12. This is 1 over 14, which is a small positive number. It's about here. And then if I go 4 to get close to the vertical asymptote, 6 over 1 over 6, this gives me 1. Alright, so I can see that this part of the function is above the x-axis and it curves like that. Okay, so this is our final graph. Alright, let me see if I can bring up a Desmos. Just ignore that. There we go. Okay, so my original function was 6 divided by x squared minus x minus 6. This is what it looks like. Alright, so this is why you need to that's not right, minus 6. Come on, you can do this. That 6 got in the wrong place. There we go. There it is. Okay, so let me resize this so you can see it a little bit better. There we go. Okay, so the Desmos graph will not show the vertical asymptotes and the horizontal ones. As I said, those are not part of the function itself. They're like the scaffold that you build ahead of time in order to kind of divide up the x-axis into regions, and you look at each of them individually so you can put the graph on there. So they won't show if you graph it with technology, but you should show it when you're graphing to do your work by hand, right? Okie dokie, let's look at the next problem. Right, there's sort of same deal here. We're looking at a rational function, finding all these details, and then with the goal to sketch a good graph of it. Alright, so let's factor this. Alright, so x cubed plus 1, this is actually a sum of cubes. Alright, so there's a formula a cubed plus b cubed factors as a plus b. A squared plus minus ab plus b squared. So this is a formula for a sum of cubes. So x cubed plus 1 cubed is our sum of cubes here. So this factors as x plus 1. And then x squared plus x plus 1. Minus. This is minus here. Alright, and this one on the bottom, we can factor out an x. And this is x plus 2. Alright, so we factor the numerator and the denominator. Now the domain. Alright, so the domain is all real numbers except for what makes these 0. So except for x is 0 and x equals negative 2. Okay. Reduce the fraction and find vertical asymptotes. It does not reduce. So both of these excluded values are vertical asymptotes. So there's a vertical asymptote at x equals 0 and another one at x equals negative 2. Now let's find intercepts. Right, so g at 0, let's plug it into this original function, is going to be 1 over 0. Alright, so this is undefined. So notice there's no y-intercept because there's a vertical asymptote at x equals 0 along the y-axis. So no y-intercept. Right. For x-intercepts, we put the top equal to 0. Let's use the factored form. When we set the whole thing equal to 0, the denominator is going to vanish because you multiply it by 0. So this gives me x equals -1. And this one does not factor. If you solve this with the quadratic formula, it's going to give you imaginary numbers. Right? If I do negative b plus or minus b squared minus 4ac over 2a, we get +1 plus or minus 1 minus 4 times 2, which is 8, divided by 2. So notice that this is -7 in here. These are not real. So that means there's no x-intercepts that comes from that part. So there's one x-intercept that comes from here, right? At x equals -1. So no y-intercepts, one x-intercept. Alright, let's look at horizontal or oblique asymptotes. Alright, so let me copy down the function here again. We're at d here. Right. So we have g of x equals x cubed plus 1 divided by x squared plus 2x. So compare the degrees of the top and the bottom. We notice that the degree of the top is exactly 1 more than the degree of the bottom, which means there's going to be an oblique asymptote. Okay, so we need to do a long division to figure out the equation, right? So the oblique asymptote needs to have the equation of a straight line, y equals mx plus b form. All right, so we're going to put x cubed plus 1 in here. We're going to fill in spaces for the missing degrees, right? It jumps from x cubed to 1. So it's kind of missing the x squared and x terms. So you put zeros in there as placeholders, otherwise it's going to mess up the division, right? So you divide the leading coefficient. You go x cubed divided by x squared. That's going to give me an answer of x. You take the x and you multiply by both of these and you write the answer underneath. X times x squared is x cubed. X times 2x is 2x squared. And now we need to subtract this from the top. So subtract the x cubed and subtract the 2x squared. This crosses out. This gives me -2x squared plus 0x plus 1. So carry down everything. Alright, then we do it again. We're going to take this leading term here, -2x squared, divided by this leading term here. We get -2. So that's the next part of the answer. This multiplies both of these terms. So we have -2x squared minus 4x. Subtract this from the top. So subtracting a negative means plus. Subtracting a negative means plus. These cross out. This gives me 4x plus 1. Alright, so now we're done because this degree is smaller than that degree. It's kind of like this number is smaller than this one. So this is the remainder. Alright, so the result of this division, right, so if I divide these out, this gives me this answer of x minus 2 plus the remainder for x plus 1 divided by x squared plus 2x. So this is the oblique asymptote. So the line y equals x minus 2 gives me the oblique asymptote. Alright. Okay. So let's build our scaffolding now. We're going to put the vertical asymptotes on here and the oblique asymptotes to kind of see what our regions of space look like. So we found that our vertical asymptotes are 0 and -2. So let's put those on there. So 0 vertical line and a -2 vertical line. Alright? And the oblique asymptote is y equals x minus 2. So this has that line has an intercept at -2 and a slope of +1. Alright, so it looks like this. So remember, these lines are not part of the function. Alright, so it's like the function doesn't actually have any points, any y-intercepts, any points on the y-axis, but we're not graphing the function now. We're graphing those oblique asymptotes, which is not really the function. It's like the scaffolding, the structure around it. Alright, let's graph the, we have an x-intercept at -1. Alright, cool. So now we're going to divide up our interval based on sort of our vertical asymptotes and our x-intercepts. Right, so we have this region right here. We got to figure out what happens. So is there a function up here above the oblique asymptote, or is there a function here below the oblique asymptote? Okay, so we need to plug in some points. So let's plug in x is close to the vertical asymptote, far away from the horizontal asymptote. Let's see what happens. All right, so let's go with x equals -3. So my function is right here. All right, we're going to plug into that. Oops. So g at -3 gives me -3 cubed plus 1, -3 squared plus 2 times -3. This is -26 9 over 3, which is approximately -9. Right, so -26 divided by 3, like -8.7. Alright, so this is here. X is -3, we get -8.7. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Alright. Now let's plug in a point. Maybe let's do, I don't know, -5 or -6. Alright, so let's do g at -6. I'm not putting in -10 because I suspect it's going to be a number that's like too low to see on the graph. Alright, so we have -6 cubed plus 1 divided by -6 squared plus 2 times -6. I'm just going to do that in the calculator. So 6 cubed negative plus 1 divided by 36 minus 12. This gives me like -8.9. -9. Alright, so 1, 2, 3, 4, 5, 6. On -0.9. Okay? So what happens here, like with these 2 points? Let's figure out what happens. So it has to do a certain thing, right? So next to the vertical asymptote, it has to go close to it and down, okay? All right, and next to oblique asymptote, it has to kind of get close to there. So this has to kind of basically turn around and then go like this and get close to the vertical asymptote. So without like too many points, you can sort of get a gist of what the function looks like. All right, now we're going to look in this region for these values of x. So I know I have an x-intercept here at -1. So let's pick values that straddle that. So like -1.5 and -0.5. we're going to figure out what those are. So G at negative 1.5 and G at negative 0.5. Alright, so this is negative 1.5 cubed plus 1 over negative 1.5 squared plus 2 times negative 1.5. This gives me, let's see, 1.5 negative cubed plus 1 divided by 1.5 squared that gave me about 3.2, and this one, negative 0.5 cubed plus 1, negative 0.5 squared plus 2 times negative 0.5. This one gave me negative 1.2. Alright, so let's go up here. And plot those points. Okay? So negative 1.5 is 3.2. 1, 2, 3. Around here. And at a negative 0.5 was about negative 1.2. Alright, so it goes up on that side and down on the other. So this is going to hug the vertical asymptote, go through the X-intercept, and then hug like this, the other vertical asymptote. Alright, so that's what it looks like in there. Alright, now we need to look at what happens in this region of X values. So you know it's going to come close to the vertical asymptote, so it's going to hug it either up here or down here. Alright, and then it could be contained in this region, getting between this vertical asymptote and this oblique one, or it could be in this region. Okay, so we got to pick some points. Alright, I'm running out of space, so I'm going to pick them in here. Let's do it in green. So I know an X value, I need an X value bigger than 0, so let's do G at 1. So this is going to be 1 cubed plus 1, 1 squared plus 2 times 1. So 2 over 3, which is about 0.7. Alright, so this gives me about 0.7. Okay, so we're in here, we're up in this region, right? And let's look at something bigger. Let's look at X equals 6. So G at 6, 6 cubed plus 1 over 6 squared plus 2 times 6. Alright, so let's see, it's 217 divided by 36 plus 12 is 48. This is about 4.5. Alright, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4.5 over here. Okay? Alright, so this means we're stuck up here. So it goes close to the vertical asymptote, then at this point it turns around, and then it hugs it like this. Alright, so that's what it looks like. Alright, let's bring Desmos in and see if it looks good. Alright, so here we go. Oh, that's the wrong one. Do I have enough? There it is. Okay, so I'm going to plug in my equation. So we have x cubed plus 1 divided by x squared plus 2x. Alright. There we are. Alright, let's blow it up a little bit, or the other way. So you can see the branch down here, and then this little one stuck between these two vertical asymptotes, and then this one here. Okay? So it looks like the one that we drew by hand. Alright, so that's what a graph of oblique asymptotes looks like. Now let's look at one more problem. So we're going to go through all the steps again. Let's factor. So this is x minus 4 and x plus 3 over x plus 5. I find the domain. So the domain is going to be all real numbers except for x equals -5, whatever makes the denominator equal to 0. Reduce, nothing crosses out. So the vertical asymptote is at the excluded value in the domain. X and Y intercepts. So let's plug in x is 0 and we get -12 over 5, which is about -2.4. So that's the Y-intercept. And the X-intercepts, if I set this equal to 0, the denominator goes away. So we have x minus 4, x plus 3 equal to 0. So that gives me two X-intercepts at x equals 4 and x equals -3. So 4, 0 is a point and -3, 0 is a point. Alright, horizontal or oblique asymptotes. So we see that the power on the top is exactly one more than the power on the bottom, which means that we have an oblique asymptote. Okay? We got to do the long division. So we're going to take x squared minus x minus 12 divided by x plus 5. Alright, so x squared divided by x is equal to x. That goes on top, multiply back in. So we have x squared plus 5x. Now we need to subtract both terms. This cancels out. This gives me -6x minus 12. Right, next round, we divide -6x by x and we get -6. Multiply this back in, -6x minus 30. We subtract, so subtracting a negative turns positive. This cancels out, and this gives me 18. Right, so this is the answer, and this is the remainder. We don't care about the remainder, but this is your oblique asymptote. So y equals x minus 6 is the oblique asymptote. Alright, let's put in the vertical asymptote. So at -5, 1, 2, 3, 4, 5. That's the vertical one. The oblique asymptote has a y-intercept at -6 and a slope of +1. Alright, I'm going to need to extend this. I think I'm going to need to extend the y-axis a little bit, because I suspect we're going to have a graph down here. So we'll just work with it. So I think this is -10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, let's do like this. Alright, now comes the time to look in each region. So my regions are here and here. Okay, so I have two different regions that I need to pick test points to see where the graph is. And so we're going to take our function. Let me write it again. So I'm going to write it here. Oops. X minus 4 times x plus 3 divided by x plus 5. Alright, this was r of x. Alright, let's put our intercepts too. So our x-intercepts are at x equals -3 and at x equals 5. X equals 4, sorry. 1, 2, 3, 4. There we go. So -3 and at 4. Alright, so let's pick some values in this region. So maybe at -6 and a -10. So r at -6 is -10, -3, -1. So it's positive 30 over this is a -30. Okay, so we're like really down here. Alright, it's like way off the chart. Let's pick -4. So we have -8 times -1 times 1. So this is +1. Oh, sorry, I meant -6. We're at -30, so we're down here. Okay, I went into the wrong region. I want -10. So -10 is going to give me -14, -7 over -5. Alright, so let's see. 14 times 7 divided by -5, that gives me about -20. So that gives me about -20, which we're here. Okay? So what's happening here is something like this. Alright? So this is off the scale. This is basically going to go down here, and this part is going to get close to the vertical asymptote on this side. Alright, now in this region, past this vertical asymptote of -5, let's pick a -4. Okay, so that's what it looks like so far. So let's pick x is -4, and there's the x-intercept and there's x-intercept, and maybe pick an x is something like bigger, maybe 8. Okay, so, and maybe let's go with, oh, we have our y-intercept. Okay, that's good. We know the y-intercept, so we know there's a dot here. Okay, I think we can already tell what happens without picking points. We have enough. Right, so we have the y-intercept is at -2.4. We have this x-intercept here. It's going to go past that point and up, hugging the vertical asymptote. Alright, and here is going to hit that x-intercept and get closer to the oblique asymptote like this. Alright, so here's our full picture of the graph. Alright, should we put it on Desmos? Alright, let's plug that in. So we had x -4 and x +3 on top. Okay, that's looking really ugly. And x +5 on the bottom. Alright, we're going to zoom out a bit. Good, so you can see our two branches. Vertical asymptote is goes through the middle of them, and then there's this oblique asymptote which makes these lines go like as a flat straight lines when they get closer to x is infinity. Alright, so that's it for this section. You're basically practicing graphing rational. Ooh! Oh, here's one more. This looks a bit ugly. Alright, let's go through this one too. Might as well. Wow, this is going to be an interesting one. Okay, so everything is factored. So let's see, the domain is going to be everything, all real numbers except for x is 0 and x equals to 4. Nothing crosses out, which means those are both vertical asymptotes at x is 0 and x equals 4. X and y-intercepts. So the y-intercept, if I plug x is 0, I get -1 and 2 and -3 divided by 0. So this does not exist. So no y-intercept because the y-axis is a vertical asymptote. If I try to find the x-intercepts, it's going to basically cross the bottom out and figure out when these are 0. So x-intercepts are going to be at x equals 1, at -2, and at 3. Alright, let's see what's happening here. So the power of the top, let's find we're basically looking at the leading coefficients. So if I cross these out, I'm going to get x cubed. If I cross this out, it's going to give me x over x squared, which is x cubed. The powers are the same. That means we have a horizontal asymptote at the coefficient of this divided by the coefficient of that. So it's going to be at y equals 1. Alright? Excellent. Okay, so we have our structure. So let's graph vertical asymptotes 0 and 4. 1, 2, 3, 4. We have a horizontal asymptote at y equals 1. Alright? And now we're going to pick some values in each region. So let's pick some negative ones. So let's say r at -1. This gives me -2 times 1 times -4 divided by -1, -5 squared. That was 8 over -25, which is -0.32. Okay, let's do r at -10. So we have -11, -8, -13 over -10 times -14 squared. Alright, I'm going to put in the calculator, and I get 0.58. Okay, so it looks like here it's 0.58 is getting close to that y equals 1. Here we're at -0.32. So what must happen is that you have this branch of the function right here. Okay, now let's look at this region. So between x is 0 and x is 4. Okay, that's the vertical asymptote. All right, we have some x-intercepts which I forgot to put in. So there's an x-intercept at y equals -2. All right, so the function must have gone through there. All right. We also have an x-intercept at x equals 1 and x equals 3. All right, let's pick x equals to 2 to see what's happening to the function there. So r at 2 is 1 times 4 times -1 divided by 2 times -2 squared. So -4 over 8, so -0.5. Right. So at 2 is -0.5. Okay, which means the function is going to go like this. Alright, now in this region, so let's have x is 5 and also x is 10. So 4 and 7 and 2 divided by 5 times 1 squared. So 28 times 2, 56 divided by 5. This gives me around 11.2. And at 10 we have 9 times 12 times 7 divided by 10 divided by 6 squared. So let's see, 108 times 7 divided by 360. This gives me about 2.1. Alright, so here at 5 we're going up to 11. And here at 10 we're about 2.1. So it looks like this, looks like this. Alright, let's check with our Desmos. So this is like higher power, so we might have missed some details. We might have missed some wiggles, but we're kind of doing our best with what we have. Alright, so on the top we're going to put x minus 1, x plus 2, x minus 3, and on the bottom we have x times x minus 4 squared, and squared. Alright, so it looks like we're not doing badly there. Okay, so let me put this between negative 10 and 10. There we go. So that's what it looks like. So again, we missed some details. I drew it like a parabola and it's a little bit crooked. But otherwise, that's kind of the general look of the function. Alright, so good. This is the last example. I'm going to finish it here. Alright, perfect.